Hello and welcome back to my channel. Today we're going to be talking about the beginnings of Unit 9. We're going to be starting with parametrics. So we're going to go into a little bit about what a parametric equation is, and then we'll talk a little bit about derivatives. So parametric equations are equations that are independent from each other but share a relationship with a third variable. A lot of times what we have is x equaling an equation and y equaling an equation, and that variable that's in both of them are shared. So it might be t for time. When we talk about a parametric equation, a lot of the times they may write it as x equals a y equals, and then sometimes they may even put it in parentheses. But when we're talking about the parentheses, these are generally going to be the points rather than the equations. So we're going to talk about sketching things by hand. We can also do it in the calculator, but for the AP test, we shouldn't have to switch modes of our calculator. We are going to learn how to do it eventually, though. So sketch the following parametric equation. X equals f of t, which is t squared minus 4, and y equals g of t, which is t divided by 2, where our t values are between -2 and 3. So what we're going to do to kind of help us out here is we are going to be making a table. Our table is going to have t values. It's going to have our x equation and then our y equation. So what we're going to do first is we are going to just mark in what t values we're going to be looking at. We're going to look at -2 to 3. So I'm going to do -2, -1, 0, 1, 2, 3 for our values here. So I'm going to focus on one equation at a time. So I have t squared minus 4. So we plug in t for t squared minus 4. So -2 squared minus 4 is going to give us 0. -1 squared minus 4 gives us -3. 0 squared minus 4. 1 squared minus 4. 2 squared minus 4. And 3 squared minus 4. Now we're going to look at y. So we have t divided by 2, so we have -2 divided by 2, which would give us -1. We have -1 divided by 2. We have 0 divided by 2, 1 divided by 2, 2 divided by 2, and 3 divided by 2. So we used t to help us look at what x is and what y is when we want a singular point, but now when we graph this, we're only going to be graphing x and y, and we're going to be graphing them like we normally would x and y. So the first thing I'm going to do is draw my graph. What I'm going to do is I'm going to do a graph that goes from -5, -4, somewhere in there to 5, and then my y values are going to be from like -2 to +2 to kind of get everything in there. So we have x, we have y. So this would be -5. So this would be +5. Make that 2. Okay. So our x value is 0. Our y value at that point is going to be -1. So 0, -1 is going to be our first point, which is going to be right here. From there, we're going to go -3, -1/2. So -3 is over here. -1/2 is going to be this point right here. -4 is 0. So -4 is 0. -3, 1/2. 0, 1. and 5 3/2 right here. So the only other thing that we need to know with a parametric equation is that we need to connect our points in a specific manner. We're only looking at -2 to -2 to 3, so we only care about those values. So I'm only going to connect our points between -2 and 3, and then we're going to put them in order of our t-value. So I'm just going to go down the list and connect them. So we connected our points in this fashion here. We didn't draw an arrow to go on, but what we are going to do is we're going to draw arrows along the line to show what direction our parametric is moving. So we started at this point in the bottom here, and then we worked our way around to get our function. So as time was moving, this is where we are with respect to time. We're going to look at another one here because we're going to use it in some other problems. Sketch the following parametric. X equals 5 minus 4t and y equals 2 plus 5t. This one doesn't give us bounds. We can't say necessarily t is going to be these values. So we just need to make a good judgment call on what values we think might be important. With transformations a long time ago, we would do about -2 to +2, and that's kind of a good amount. But we could also probably get away with doing less depending on what we have. So if we do -2 to +2, this gives us a good spread. So -2, when we plug it in for x, we have 5 minus 4 times 2. This is going to give us 13. When we plug in -1, 5 minus 4 times -1 is going to give us 9. 5 minus 4 times 0. 5 minus 4 times 1, and 5 minus 4 times 2. Then we plug in all of those same t values in for y. So 2 plus 5 times -2, 2 plus 5 times -1, 2 times 5 plus 0, 2 times 5 plus, or 2 plus 5 times 1, 2 plus 5 times 2. And then we graph these values. So once again, I'm looking at x values that are between like -4, -5, and 13. I'm going to leave 13 off of this one for right now because we picked these t values, and 13 is going to be hard to cram on this graph. Our y values are looking like they're between -8 and +12. Since I'm going to get rid of 13, I can get rid of -8. So we're really looking between -4 and 12. So I'm going to make my graph kind of look like this. So my x-axis is going to be here. My y-axis, we'll do it here. And then I'm also going to go by 2s. So I have 2, 4, 6, 8, 10, -2, -4, -6. And we're going to do 2s on the y-axis as well. 2, 4, 6, 8, 10, 12, -4. Okay, so I have 13, -8, which I'm going to skip, but I have 9, -3, so 9, -3 is going to be right here. 5, 2, so 5, 2, 1, 7, so put it here, and -3, 12. And if we connect these points, we are going to notice that they connect in a straight line. And because we didn't tell the parametric to be in a certain spot, we're going to have arrows on both ends. And then we would also have arrows to show what direction we were going. So if we look at our values, x and y look like they're going backwards on the x-axis, so towards the negatives x, but the positive in y. We can change between parametric and what we call rectangular form. Rectangular form is that XY form that we're really used to, so we don't have to do a lot there. But, you know, we do have to do something. So we are going to take the equation from that example right above, and we're going to use it to write our equation in rectangular form. So the two things that we have are x equals 5 minus 4t and y equals 2 plus 5t. So rectangular form is y equals. So what we want to do is we want to replace t with x in that y equation. So what we're going to do is move around what we have. So I want to get t by itself. So I'm going to subtract 5 from both sides. And then I'm going to divide both sides by -4. To make this easier on myself, I'm going to go ahead and move around what I have. So if I take that negative, I can also say 5 minus x over 4. And we're going to take this and we're going to plug it into the equation that we have. So our equation right now is y is equal to 2 plus 5 times. We have this 5 minus x over 4. If we actually simplify or not is kind of dependent on the question. We can simplify this, but we don't necessarily have to. So if we simplify this, we're going to do what we would normally do. So distribute out that 5. So we have 5 times 5. And then if I have dividing by 4 on everything, I can also divide each individual piece by 4. And then I can combine like terms. 2 is the same thing as 8 over 4. So I have 8 plus 25 still over 4. So I have 33 over 4 minus 5x over 4. We can do this for a lot of things. One of the biggest things that we're going to do is look at trig functions. We can have theta instead of t, which would make sense for things that have to do with angles. And when I see you guys again in class, we'll look at how we would put this in the calculator. So let's look at what we have for this one. So this one's a little bit different when we talk about changing this parametric into a rectangular form. And the reason why is because we have these trig functions. So we have example number 3 is going to be x equals 3 cosine theta, y is equal to 7 sine theta. For this one, we want x and y to be in an equation together, but we don't necessarily need it to be y equals. The problem with some of these is in order to get theta by itself, x or y would be in this kind of weird function. So if I were to get cosine by itself, I would have x over 3, and I would take the cosine inverse of that equation. So I'd have the cosine inverse of x over 3. If I plug that in, we would have 7 sine of cosine inverse of x over 3, and that's just not very helpful as an equation. It also doesn't give us a very accurate equation either. So we are still going to move around, so all of our cosine and sine are by itself. So we're going to do the division by 3, the division by 7. And the equation that we want to plug it into is one of our Pythagorean identities, and that Pythagorean identity is sine squared theta plus cosine squared theta is equal to 1. Well, sine squared and cosine squared can be written as sine of theta squared cosine of theta squared. And we have relationships over here that says sine of theta is the same thing as y over 7, and cosine of theta is the same thing as x over 3. So we're going to go ahead and plug those in. So sine squared is, oh my gosh, y over 7 plus cosine theta squared, which is x over 3. So we have y over 7 squared plus x over 3 squared, and then we may square each of those things. So if I square y over 7, we get y squared over 49, 7 squared, plus x squared over 9, 3 squared. One of the things that you may notice is that this looks like the equation for a circle. So this has some similarities here that we can see, which makes sense because sine and cosine have that kind of relationship.